Today's video is on integration using residues. In today's video, we are going to use the method of contour integration to prove that integral 0 to 2 pi d theta by 1 plus a square minus 2a cos theta is equal to 2 pi by 1 minus a square, where 0 less than a less than 1. So here, as usual, we have to put z is equal to e power I theta. Clear? So what is e power I theta? This is cos theta plus I sin theta. And if I take modulus on both sides, so this is modulus of cos theta plus I sin theta. So which is equal to mod z value is equal to root over this is cos square theta plus this value is sin square theta. And therefore mod z value is equal to, so here mod z value is equal to 1. So we got the region that is circle with center 0 and radius 1. So this is the region for z is equal to e power I theta. So we need d theta value here. How we'll get d theta? As we have z is equal to e power I theta. See, z is equal to e power I theta. Clear? And now if I differentiate on both sides, dz is equal to e power I theta again, and I into this is d theta. So e power I theta is nothing but z. The value here is z. Clear? And therefore dz is equal to this is zi into d theta. Therefore our d theta value is equal to dz by this value is zi. Clear? So we got the value of d theta as dz by this is zi. And next thing, we need cos theta value. For getting cos theta, see here, for getting cos theta value, what we have to do, cos theta can be written as, this is e power I theta plus e power minus I theta by 2. So cos theta is equal to, this is z plus this is z inverse by 2. Therefore, cos theta is equal to, this is z plus this is 1 by z by 2. So cos theta is equal to, so cos theta value is equal to, this is z square plus 1 by 2z. So we got cos theta as z square plus 1 by, this is 2z. This is dz and this is mod z is equal to 1. Clearly, if you see, so we got the region as a circle with center 0 and radius 1. And next thing, d theta value we got as dz by this value is zi, and we got cos theta value as, see here, cos theta value as z square plus 1 by this value is 2z. Clear? Now I am going to substitute in this integral. See here, the integral here is nothing but this is integral 0 to 2 pi. So this is integral 0 to 2 pi. This is d theta by 1 plus a square minus 2a into this value is cos theta. See, this can be written as integral 0 to 2 pi. In place of d theta, I am writing dz by this is zi by this is 1 plus a square minus 2a into cos theta value is z square plus 1 by the value here is 2z. And see, this can be written as integral, this is 0 to 2 pi, this is dz by the value, it is dz zi into, see here, if I cancel this 2 and take z as LCM, see here, if I take z as LCM, this will be z into 1 plus a square minus a times of this value is z square plus 1. Z square plus 1. Now, if I cancel the z, see, this will be integral 0 to 2 pi, this is dz by I times of this is z plus, if I multiply, this will be z plus, this is z a square minus a z square, this is minus a, this is minus a, the value here is minus a. So this will be integral 0 to 2 pi, this value is dz by I times of, this is minus a z square. So if I take, see here, if I take z common here, this will be plus z times of, so this is z times of this value is 1 plus a square and this is minus a. This value is minus a. And clearly, if I take minus common from these, this will be minus I times of this is a z square minus z times of 1 plus a square plus a. Clear? Now see what is our f of z from this. So f of z is clearly written as, so f of z value is nothing but integral f of z into dz. So this will be 1 by minus I times of, this is a z square minus z into, this is 1 plus a square plus a. So in order to get the poles, what we have to do? So we have to equate the denominator to 0. That is minus I times of, this value is a z square minus z into 1 plus a square plus a value is equal to 0. So if I send minus I to other side, so what remains here? This is a z square minus z times of, this is 1 plus a square plus a is equal to 0. So as we have a formula ready here as minus b, in order to get the poles, this is, or roots, minus b plus or minus root over b square minus 4ac by 2a. So this is a value, this is b value, and this is a c value. So if I substitute, z value will be, see here, z value will be minus b, that will be plus 1 plus a square plus or minus root over b square, that is 1 plus a square whole square minus 4 into a into c, so which is equal to a square by this value is 2a. So z is equal to, this is 1 plus a square plus or minus, so if I expand, this will be a square plus b square plus 2ab minus 4a square by, this is 2a. So z is equal to, this is 1 plus a square plus or minus, this is 1 plus a power 4 minus 2a square by, the value here is 2a. The value here is 2a. So this can be written as, z is equal to, see here, z is equal to 1 plus a square plus or minus, this is 1 minus a square whole square by, the value here is 2a. So if I cancel this square and root, our z value is equal to, this is 1 plus a square plus or minus 1 minus a square by 2a. A square by 2a. See, the first pole here is, this is 1 plus a square plus 1 minus a square by 2a, and here the next thing is 1 plus a square. If I take minus inside, this will be minus and this is plus by 2a. Now I can cancel these two and z value is equal to 2 by 2a, and here if I cancel minus 1 and plus 1, z value is 2a square by 2a. Got it? And see, if I cancel these two, z value is equal to, the pole value here is 1 by a, and here if I cancel, z is equal to a here. So these are the simple poles. So z is equal to 1 by a, and clearly z is equal to a are the two simple poles. These are simple poles. See here, we have to check whether these two poles are within or on or outside the given region. So here the given region here is nothing but mod z is equal to 1. So here the given region here is mod z is equal to 1. And clearly it is also given that 0 less than a less than 1. So I'll take these two, that is clearly mod z is equal to 1 is the region and 0 less than a less than 1. See, what is mod z less than 1? So this is nothing but a circle with center 0 and radius 1. So this is minus 1. So this is I. So this is minus I. So a is, so if you see a is less than 1. If you see, so a is less than 1. So it is within this one. So a is less than 1. 1 by a is greater than 1. So 1 by a is outside, which is greater than 1. So this is not the pole. So this is the pole which is within the given region. So we have to find the residue at z is equal to a, and so this is not needed. So this is not needed, and this pole is the only pole which lies within the region. So I am going to find the residue for this. So for finding the residue, as usual, that is the formula here is residue of f of z at z is equal to a is nothing but, this is limit z tends to a, this value is z minus a into f of z. F of z. Now here limit z tends to a. So this is limit z tends to a, as it is the interior pole. This is z minus a into f of z. So what is our f of z here? So let me show you. Our f of z value is this one. As see here, this is 1 by minus 1 I times of, this is minus a z square. So this value is a z square minus z into 1 plus a square, z into 1 plus a square plus a. Clear? And now see here, I am going to substitute. This will be limit z tends to a. This value is z minus a by minus I times of. See here, this is a z square. So if I multiply, this is z minus z a square plus a. And next, this value will be limit z tends to a. This is z minus a by minus a times of. So if I take z common, so this will be az minus 1. So here if I take minus a common, this will be az minus 1. So this will be az minus 1. And clearly this will be limit z tends to a. So this value is limit z tends to a. This is z minus a by minus I times of. So if I take this az minus 1 common, so this will be az minus 1 into the remaining one z minus a. Clear? So this is our f of z, and now I can cancel z minus a from the numerator as well as the denominator, and again I can substitute here as a. So this can be written as limit z tends to a, limit z tends to a. This value is 1 by minus I times of. If I take a common, this will be z minus 1 by a. Z minus 1 by a. Now if I substitute in place of z as a, this will be minus I times of a into a minus 1 by a. So this is minus a I times of, this is a square minus 1 by a. So I am cancelling a here, and this is, if I send minus inside, this will be I times of 1 by a square. So this is nothing but residue of f of z at the interior pole z is equal to a. Clear? Now I am going to apply the residue theorem. So what is the residue theorem? Statement states residue theorem. So according to the residue theorem, we have integral f of z into dz is nothing but, this is 2 pi I times of, this is 2 pi I times of sum of the residues of the interior poles. Sum of the residues at the interior poles. Here our residue value is nothing but, so this value is integral 0 to 2 pi. So this is integral 0 to 2 pi. This value is d theta by 1 plus a square minus 2a cos theta is equal to 2 pi I times of the residue at the interior pole, that is I times of 1 minus a square. Now if I cancel these two and if I multiply, therefore integral 0 to 2 pi, this is d theta by 1 plus a square minus 2a cos theta value is equal to 2 pi by 1 minus a square. 2 pi by 1 minus a square. Here 0 less than a less than 1 is the condition. So this is the final answer. This is how we have to solve, and thank you so much for watching and staying till the end, and let me explain you once again. See here, first of all what I have taken. So this is the question. So we have to show that integral 0 to 2 pi d theta by 1 plus a square minus 2a cos theta is equal to 2 pi by 1 minus a square. Here it is the condition. So first of all we have to put z is equal to e power I theta, and after taking modulus on both sides, we got the region with circle with center 0 and radius 1, and here we need d theta value. For that I made I made a derivative on both sides, and d theta value is equal to dz by za, and cos theta value is this one. So after getting all the three values here, and this is the integral, in place of d theta is dz by za, and in place of cos theta is this one, and after taking LCM and cancellation, and after taking z common here, and after bringing minus outside. So this is f of z here. So f of z value is this one. So as you know that if you equate the denominator to 0, we'll be getting the poles for the given function. So after equating, so here is the formula, that is minus b plus or minus root over b square minus 4ac by 2a. So after calculating and substituting, so we got the pole values as, so here are the pole values as z is equal to 1 by a and z is equal to a. Clearly, if you see, the region here is mod z is equal to, so here mod z is equal to 1. So this is the region with circle 0 and radius 1. So here it is given that a is less than 1. So a is within the region, that is which is less than 1. And here a is less than 1, therefore 1 by a is greater than 1. So it will be outside the given region. So therefore the residue for 1 by a is not needed and z is equal to a is only needed. So the residue value is nothing but z minus a into f of z. So as we have f of z value ready here as this one, and after substituting f of z value and see here and expanding here and taking az minus 1 common, so we got az minus 1 into z minus a, and now I can easily cancel numerator and denominator, and after taking a common from this, z minus 1 by a. So after substituting z is equal to a, I got a square minus 1 by a, and this is how we have to solve. After sending minus inside, this will be 1 minus a square. So according to our residue theorem, integral f of z dz is nothing but 2 pi I into sum of the residues at the interior poles, that is 2 pi I into the residue value here is this one, and after cancelling, so this is the final answer. And thank you so much for watching. If you have any doubts, please leave a comment below, definitely I'll solve. And thank you so much for watching. If you really like this video, please pass it on to your friends.